So hi again. Welcome to part 2 of lecture 3, and we will continue with the probability mass function. So in the previous part, we see how we can assign random variables to make the process easier, and even the base random experiment is continuous. We can assign some discrete numbers, and to make the process simple to follow. Okay, and here. The most important way to characterize a random variable is through the probabilities of the values that it can take, right? So if you remember, we defined the random, So if you remember the previous lecture, we said that the random variable x can take some values, right? So if x, any possible value of x, so this x can be different numbers, right? Different values. The probability mass of x is the probability of the event x is equal to the small x, consisting of all outcomes that give rise to a value of x equal to x. So that's mean, based on your interest, this x can take some different values. And the same number will be associated all of these different outcomes, right? And this function, the function that maps the set of all possible value of x to their probability masses, is called the probability mass function. So I can use this notation. The probability of the capital X subscript in x is equal to probability of v in omega. So we will work with a subset which is belong to omega, and the values of x, the xv, will be equal to x, the small x, and this is give rise to the value of this one. Okay. So this can be a little bit confusing, but actually the concept is extremely easy. When we solve when we solve an example, you will understand in a better way. But let's look at the calculation of the PMF of a random variable x. So as we say, the capital X is equal to x, and this x can take some different values. So to collect all possible outcomes that give rise to the event x is equal to x. Okay, that will be valid for this equation, this equality. And then add their probabilities to obtain the probability of capital X. This is the probability of all possible outcomes. In here, just to make it more concrete, let me give you an example. Let's say we toss 2 coins. What can be the result? Let's say, which is head, tail, and tail, head, and the tail, right? So let me write the probability mass function of all possible outcomes, right? So let's say the x is equal to x, and let's say my interest is the number of heads, the number of upward phase will be head. So my x is x can be capital X. Sorry, just let me flip this part. This is this one. Okay. This is the random variables, and this small x is the values that my random variables can take. Okay, so what the x can be? It can be 0, okay, 0 hat, 1 hat, and 2 hat, right? So, which is not possible to get in other no values. So, if x is equal to 0, I can say that the probability of capital X is equal to 0. What? So, which outcomes gives rise to this one? I mean, this one, x is equal to x 0. Okay, let's say. So only this one, right? So I have just one subset in my sample space that is valid for this condition, this equality. So because this is a uniform model, I can simply calculate the probability by this formulation. Sorry, what happened? So this formulation, right? That is a probability of X, probability of A. So I have only one outcomes, which is a tail and tail, that will valid for this equality, and this will be 1/4. If x is equal to 1, in this case, my probability is going to be 2/4, right? Because there are two outcomes valid for this equality, and I have four possible outcomes, so which is going to be 2/4, which is 2. And this one is x2 is again only I have one outcomes, and this will be 1/4, right? So this is the probability mass function, and that's map the all possible outcomes to some discrete numbers, right? So this is the PMF. So let's look at another example and how we calculate the PMF. And let's say I have a four-sided field die, and I'm gonna roll it 2 times. Okay, rolling 2 times. So my interest is my random variable will shape around the maximum roll. So I will get a pair, right? When I roll 2 times, I will get pair like A and B, and X will be equal to max of A and B. So let's look at only this one. So in this case, I'm saying that my x is equal to 2, right? So which points I need to look at here? This one, and this one, right? So all these points are associated with the number 2. To calculate the probability, just think inversely and go back to your sample space. And in my sample space, there are 16 different points, all these points, and 3 of them associated with the number 2. So I can simply write the 3, and the probability of Px is equal to 2 is going to be 316, right? So this is a 360. So let me do one more here, and you can do rest of them at home. Let's do this one. This is the 3 one. So I think this point and this point, this point, this one, and this one, 1, 2, 3, 4, 5. These 5 points are associated with the 3, right? So in this case, my interest at the maximum roll, I mean the x is equal to 3. Okay, and I need to look at this probability. So 5 points are associated with the number 3. So again, I have 5 for these random variables. There are 5 different subsets, and I have 16 different subsets. So this will be my probability. Okay, so if you summarize the thing, we can say that if you want to calculate the probability mass function, first think that what values uh, x can take. Okay, the small x can take. So it can take the different values, but these different values can be associated with the same number. In this case, you will just look at how many numbers, how many different subsets is associated with that x, and then you can calculate the probability as we did in the previous lectures. So this is the this is the example we did here. Okay, or you can just here you can look at. I mean, these things can be written in a simple way. We can take the probability of x is equal to 104 if x 0, 102 if x is 1, and 104 if x is equal to 2. I can also write, I can write in this way to make it the thing simple. So let's look at another example. In this example, we have 2 independent tosses of rolling of a pair die, and let y be the sum of the rolls. So the sum of the rolls is my interest, right? And the random variable y will be shaped based on my interest. Okay, so the summation will be between 2 and 12, right? Because the smallest pair of die is 1, 1, and the biggest pair is 6, 6. So the summation will be between 2 and 12. So let's do it for a few possible outcomes. Let's say we are looking y2. So there is only one subset, which is 1 and 1, that will give us the summation as 2, right? There is no any other possible outcomes. And what is the total outcomes? The total pair is, sorry, not this one. So we have 36 different pairs, right? Remember the die examples. So out of 36 one, we have only one outcomes that is valid for this equality. Okay, so that's why my probability would be 1 or 36, right? So let's look at the same thing for this one, by the way. There is only one pair, which is 6 and 6. that is valid for this equality. The summation will be 12. So there is no any other pair that their summation will be 12. So there is only one. That's why the probability is 1 over 36. So let's look at the, let's say, this one. So in this case, I'm saying that my interest is the sum of the rows will be equal to 4, right? So what is the possible subsets which coming from the omega, which is a 1, 3, 3, 1, I think, right? And 2, 2. So is there another pair of rows, pair of numbers that summation will be 4? I think no. So in real sample space, there are only 3 subsets. These are. So we take the inverse and we go back to the sample space to count the number of possible subsets that gives rise to this one. So we have 3, and the total pairs are 36, right? So this is the number of all pairs form our omega. So and that's why the probability of this one is 1 over 12. So if I write it explicitly, we can say that this is 4 is 1 over 12. So this is the probability mass function for this example. So let's look at some details, and we will omit the link to the underlying probabilistic model when possible. So if you have a probability mass function, you don't need to look at the probabilistic model of your problem. You can calculate any of the events or any of the subsets of the omega, the probability of any subset of omega if you calculated the probability mass function. And also, we will omit some braces from the event and set notation when possible to make the things easier, okay? To make them easy to follow. So we will use this notation instead of much more correct one, this one, okay? So in this case, this says these are the subsets. I mean, these are the elements in omega. We can think them as a subset, and the subset will give rise to this one. But instead of using this one, we are going to use this simple notation. P x is equal to x, and x can take any different values, and this different values will belong to omega, right? Oops, sorry. Sorry. Let me correct this one. Let me correct this one. So which is we are going to use this one, and this is actually a function, and the input of this function is actually this one, and this one is coming from the omega, right? For example, in tossing a coin example, like tossing a coin 2 times. What was our omega is hat, tail, hat, and tail, right? So let's say I'm looking for 2 hats. My interest is 2 hats, and otherwise it's 0. Okay, so if I want to calculate, if I say that x is 1, okay, probability of x1, that's mean the small x is 1, right? And when I go back to my sample space, because I can write this explicitly like that, x hat hat is equal to 1 actually, right? And this is the x. So this is v, and this v is in omega. It's a subset of the omega. But instead of using these things, sorry, we can simply use that one, and we can interpret this one. This is the value random variables can take, and if we think inversely, these numbers is associated with some subset in the omega. Okay, and we will do the same thing for the subsets. It's we will use the probability of x in S instead of more correct notation, that one, which is again the same logic. And this is x, I mean the v in omega such that x v in S. Okay, and in this case we are using the subsets of the omega. This can be any subset, and we can make it simply for this one. So you can think the tossing coin example again, and let's say the x v in S hat, right? And this v actually is coming from the omega, so which is the subset of the omega. So you can omit these notations, and we can simply use that one. Okay, so our random variables is the element of any subset of the omega, and also we can say that for this one, the x can take, or our random variable can take any values. Okay, and this value is actually associated with some subset of the omega, or some elements of the omega. Okay, so let me continue. So the sum of all possible outcomes, sum of the probability of all possible values of the random variable will be 1, right? So in the tossing coin example here, we can let me write that one. So hat, tail hat, and tail. So the all possible the values it can take, like getting hat, right? I mean, what was 0, 1, and 2, we can get 0 hat, 1 hat, and 2 hat. What was the probabilities is 1, 4, 1, 2, and 1, 4, right? So 1, 4, 1, 2, and 1, 4. If you sum all these things, you will get the 1. Also, you can deduce this thing from the probability axioms, because the union of all possible subsets will create our omega, right? And the probability of omega, if you remember, is equal to 1. So in the same way, we can consider the collection of the possible values will be the same. We can consider the collection of all possible values as this equality, right? Probability of x in S. So the x will take the values in subset, okay, in one of the subsets. So which will be equal to any x which fall into this subset. Okay. I hope that's clear. Let's do it again. The probability of random variable x, which is belong to subset of S, will be equal to sum of the individual probabilities of the random variable x that will take the values from that subset. Okay, so if x, for example, if x is the number of heads obtained in two independent tosses of a fair coin, what is the probability is what is the probability of at least one head? So this is our omega, right? This is our omega. Head, tail, tail, head, and head, tail. So what's my interest is at least one head. So S, the subset will be a head, tail, and the tail head, right? So I am looking the probability of this one, right? This one. So simply I will calculate each probability, and some of them will be equal to this one. So by using this random variables, I can say that if I look at the probability of x is greater than 1, right? I can, so yeah, if I calculate the probability of x in which the small x will be greater than 1. So that's mean, actually, if I open this part, that's mean I will calculate the x is equal to 1 plus the x is equal to 2, right? So what was the probability of this one? It's 1 or 2, right? And what was the probability of this one? This one. So 2, and that will give us 3 or 4. So what we did, we summed the probability of each possible the values that x can take. In the case of x is in S, and this will give us the probability of random variable x, which is in S. Okay, so you can also use this one. So this is the solution of this one, and this is the solution of this one, I think. Okay. Yes, let me. Yes. So this is the solution of this notation, or proof of this notation, and this one is the notation, the proof of this notation. Okay, or you can check yourself again. Okay, so in the next part we will continue with the cumulative distribution function, which is also useful in many different problems. Okay, I'll see you in the next part.